Good morning, everyone, and welcome to this session on prioritizing technical debt. This is a broad topic, and I have a lot of stuff to cover for you today. So I want us to jump right in and start by uncovering the forces we have to balance when building large-scale software systems. And I do think that these forces are very well captured in something called Lehman's laws of software evolution. So let me ask you, how many of you have heard about Lehman's laws? Not so many. That's good. I got something new for you. It's perfect. So Lehman's laws, they are pretty fascinating because they are old. They were written down in the 1970s, early 1980s, and they are not that well known. So I try to do my best to popularize them. And today I want to show just two of those laws to you here now. So let's start with the first law and see if it resonates with your experience. So the first law of software evolution is the law of continuing change. Well, Lehman says that the system has to continuously evolve and adapt, or it will become progressively less useful over time. Do you recognize this? Yeah, this is the very reason why we keep adding new stuff, new features to our existing products, because we need to keep them relevant. We need to respond to competitors and user needs. What I want you to do now is to note that in the second law of software evolution, we have some kind of conflict, some kind of tension between these two laws. Because the second law is the law of increasing complexity. Well, Lehman claims that as a system evolves, its complexity will increase unless we actively try to reduce it. So, do you see the tension between these two laws? On one hand, we have to continuously evolve and adapt our system, but as we do, its complexity will increase, which makes it harder and harder to respond to change. So this is a vicious circle that we need to break. And the problem is, when we fail to do that, we tend to see the symptoms more than their true root cause. And we tend to see the symptoms differently depending on who we are, what our role is. So what most business leaders and technical leaders tend to see is symptoms on the roadmap. We might experience long lead times. It simply takes longer and longer to implement a new feature. We might also notice, as a consequence, a lack of predictability. That is, it becomes incredibly hard to guess how long it's going to take to implement a particular story. What our end users tend to see are symptoms on the external quality of the code. They tend to see this. They tend to see bugs. And the real issues tend to remain largely hidden and opaque. So how can we shine a light on issues like code quality and technical debt? Well, one obvious way of doing this is to start to quantify technical debt, right? We could simply put a number on it and see if our debt grows or shrinks. So this is something I've seen done many, many times. So as part of my day job, what I do is I work with code analysis. So I go to different organizations, I analyze the code, I try to give my recommendations. And when I started to do this, it's a little bit more than 4 years ago now, one of the first clients I visited, they had done something pretty fascinating prior to my arrival. They had used a tool capable of quantifying technical debt based on how the source code looked. So they had taken this tool and thrown it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. Now, 4,000 years of technical debt, I always like to put things into perspective. So 4,000 years ago, that was here. That's the start of recorded history through the invention of writing. So on a side note, I always get curious, what kind of program language did they use? Most likely a Fortran, right? Yeah. So anyway, I want to point out that I'm well aware that those 4,000 years of technical debt, it grew in parallel by having hundreds of developers working on the code base. So it might actually be accurate. The question is, how useful is it? How do you act upon that data? So this is where it starts to become dangerous, because this is also something I experienced in many different organizations. When you try to quantify technical debt based on how the source code looks or any properties of the code, what tends to happen is that the first time you do that, you end up with lots of information. right? You might have thousands of potential problems in your code base, quality issues. So how do you act upon that mass of data? Well, the first thing that happens is that we start to look at the different categories. So we might think that maybe the tool recommends some recommendations, right? So let's skip them. We don't have any time to improve something here. And then we see warnings. All right, maybe they're not that important, right? So let's push them to the side. And we tend to focus on the most severe category. And even when we do that, I've seen lots of existing applications where running a static analysis produces like 5, 6, 7,000 major issues. And at some point, the symptoms of technical debt, they tend to become too pressing, so the organization needs to act upon it. And the way many organizations tend to act upon this is by putting a quantitative goal on it. So maybe they say things like, all right, we have 7,000 major issues. Let's invest 3 months into bringing that down to 5,000. And when I hear something like that, I always advise against it. Because to me, going from 7,000 major issues down to 5,000, you know, it's a little bit like choosing to jump from the 5th instead of the 7th floor. It's most likely not a good idea. And the reason I say that is because we really have to consider what kind of behavior we reinforce by putting a quantitative goal on technical debt. Because what is going to happen? Well, with a quantitative goal, people like us, developers, we're going to optimize for what we're being measured on. So that most likely means that we're going to pick not only the simplest tasks, but we are going to pick tasks that we are comfortable with, that we are familiar with. And that also means that we lack the most important aspect of technical debt. We lack the business impact. There's no link to the business impact in a quantitative goal. So I think that trying to put a quantitative goal on technical debt, I think it's actually dangerous, right? In the best case scenario, you're just wasting time. But what's more problematic is that you miss an opportunity to invest your time into doing something that could really, really have an impact on your business. So what I want to show you now is that quantifying technical debt, it's possible, it might be interesting, it's most likely depressive, but it's not actionable. And okay. This is going to be interesting. No tweets, please. All right. So trying to get back on track, quantifying technical debt is not necessarily actionable. And at the same time, it's really important because we always have this trade-off where we need to balance improving existing code versus adding new features, right? So it's an important topic that we need to stress. But how do we do it? How do we prioritize it? Well, those of you who might have been to one of my previous sessions or maybe even read one of my books, you know that I'm a big fan of version control data. I know, we all have our odd hobbies, right? This one is mine. And the reason I'm so fascinated by version control is because version control data is a wonderful data source. And I find it so fascinating that in the software industry, we have been using version control for decades, and we have used this mainly as some kind of overcomplicated backup system, and occasionally as a collaboration tool. But in doing so, we have built up this wonderful data source. So what I'm going to do today is to show you some case studies on how we can apply version control data to prioritize technical debt. And I want to start by showing you a system, a real-world code base that I think a lot of you might actually carry around in your pocket as I speak. I'm talking about this. I'm talking about Android. More specifically, I want us to look at a part of Android known as the Platform Framework Base. So the Platform Framework Base in Android, it's a big code base, right? 3 million lines of code, lots of developers. And the visualization you see here is something I call a hotspot analysis. So I want to walk you through this so you know what you see. The first thing I want you to focus on are those large blue circles. You see the ones that blink on screen there? Each one of those represents a top-level component, a top-level folder. So this is a hierarchical structure that follows the folder structure of your code. Now, it's also interactive, so we can zoom in to any level of detail we're interested in. And when we get to the lowest level, we see that each file with source code is represented as a circle. And we see that the circles have different size. So let's have a look at those dimensions. So the number one hotspot in Android right now is something called an ActivityManager service. Isn't that a beautiful name? Right? Let's consider that for a moment, right? Activity could be something from the problem domain, but then we have two more or less non-descriptive words, manager and service, that each one in isolation indicates a unit with low cohesion, and we combine them, right? I'm curious what we're going to find inside this one, because we are going to look into it. Now, let's get to the dimensions here. You see that the files have different size, the circles. That's because size is used to represent code complexity. Now, how do you measure something like code complexity? That is, how hard is that code for a human to understand? Well, you might have heard about things like cyclomatic complexity, Halstead's volume metrics. And truth is, you can use any of those metrics that you have easy access to, because what they all have in common is that they're equally bad. It turns out, if you look at the research, just controlling for the number of lines of code means that those more elaborate metrics don't add any further predictive value. So what I tend to use is just the number of lines of code, because this, and let me repeat it, this is not the important dimension when prioritizing technical depth. And the reason I say this is because code complexity has this property that code complexity is only a problem when we need to deal with it, right? So we need to figure out, all right, we have some potentially complex code. Do we actually have to work with it? And this is data that we can pull out of a version control system. We can look at things like the change frequency. How often do a developer go into that code and make a modification to it? And we can simply count the number of commits. And in the technical depth terminology, I like to view code complexity as a principal. That's the loan we have taken on. However, the change frequency, that's what I use as a proxy for interest rate. And when we combine these two, we're capable of identifying hotspots. That is complicated code that we have to work with often. So at this point, we need to dig a little bit deeper and actually look at the code. And what I tend to prioritize when talking about technical depth are a number of predictors of code that's not only going to be expensive to maintain, but also at risk for defects. And what I tend to find and what I tend to look for are things like cohesion, right? If you have too many responsibilities stuffed into that module, it's going to have many reasons to change. And as a consequence, it's going to attract many different developers, which might lead to coordination issues in that code. Also look for certain low-level patterns, like, for example, deeply nested logic, right? You know, if statements inside if statements inside if statements. Do you know how many percentage of all defects come from constructs like that alone? Roughly 20%, right? So I tend to look at the code and I try to form an opinion if this is likely to be a big problem. In this case, I can spoil it and say that, yes, that code ticks all of those boxes. So what I do next is that I try to figure out, all right, maybe this code is a hotspot because the organization already knows about it. So maybe the developers are doing a lot of work in that part of the code because they're refactoring and improving it. To answer that question, we can use a different technique that I call complexity trends. So what I do here is I simply go to the version control data and I pull out each historic revision of that piece of code. And then I measure the code complexity, typically using one of the simpler metrics like cyclomatic complexity or nested logic, something like that, and plot it over time. And for reference, that's the red line. The blue line is simply the accumulation of lines of code. So when we view this graph, we see that the number of lines of code seems to grow steadily, which might be a problem in itself. But it's definitely a worrying sign when the complexity seems to increase at an even steeper rate. So what this means, if we take a step back, is that we have a piece of code that we need to work with all the time. That code has some quality problems, and when we work with it, it gets worse and worse and worse. So this is the kind of code we need to act upon. Now, let's put some numbers on it. The ActivityManager service hotspot consists of roughly 20,000 lines of code. It had 74 developers contributing to the same file just over the past 3 months. At the same time, we saw that previous slide indicated that this is code that we really should refactor, right? There's likely to be a very big payoff here because we work with it all the time. So who would like to have that refactoring task? A few brave souls, that's good. I would actually advise against it because I think it's dangerous to take on refactoring and redesigns at that scale. Because what's very likely to happen is that if you look at that second number, it's nothing to do with the code, but look at the number of developers touching that code. So what's going to happen if you decide to refactor this, then you're going to branch out. You're going to work on that branch for 2 months, and you're never, ever going to be able to deliver it back. Because in the meantime, your colleagues have been adding lots of new features to the code, right? Remember the law of continuing change. So we need to do better. We need to come up with much more specific refactoring insights. And to do that, I use a technique I call Hotspots X-ray. So what I do here is that when I come across a large hotspot like that, I take that code, and I parse it into separate functions and methods. Then I look at the version control data, and I see where do each commit hit over time. And I sum it up, and I get hotspots on a function level. Let's have a look at that. Let's do an X-ray of ActivityManager service. Now, this is what I tend to use to select the first prioritized refactoring. And in this case, we see that the hotspot on a function level inside ActivityManager service is a method called handleMessage. We see that handleMessage has been modified 96 times just over the past year. So roughly twice a week, some of the developers are inside that code. If we look at the lines of code of that method, we see that it consists of 500 lines. That's a lot for a single method, isn't it? It is. But it's much less than 20,000 lines of code, which was the size of a total hotspot. And it's definitely less than 3 million lines of code, which was the size of a total code base. So more important, we are now on a level where we can start to act upon this information and do a focused refactoring based on data from how we, as an organization, actually works with the code. So I want to show you some statistics to explain why hotspots work so well to prioritize technical debt. The main reason they work so well is because all code really isn't equal. So please have a look at the following graphs. This is some of the most important data I'm going to show you today. What you see here are examples from 3 different systems, but they all show the same kind of data. On the x-axis, you have each file in the system, and those files are sorted according to the change frequency. That is, how many commits, how much work have you done in each one of the files. And the number of commits is what you see on the y-axis. Now, if you look at those 3 examples, you see I've chosen examples from 3 completely different code bases, targeting different domains, written in different languages, by different developers, different organizations, different lifetime span. Everything is different. And yet, they all show exactly the same distribution. They show a power law distribution. And this is something I found in every single code base that I've ever analyzed. And I probably analyzed around 250, 300 code bases by now. So this seems to be the way that software evolves. And this is important to us, because what this means is that most of our code is going to be here in the long tail. So it's code that's rarely, if ever, touched. So unless we have some very specific contextual knowledge, spending time refactoring code in the long tail is usually not a good investment in the short term. Most of our development activity, on the other hand, is going to be in a very small part of the code base, at the head of the curve. And that's what hotspots do for us. They help us identify those intersections between high development activity and technical debt. But hotspots do one more thing for us. And what they do is they help us put code quality into context. And last year, I published a book called Software Design X-Rays, and I want to show you my favorite chapter of that book. I'm really happy with the title here. I claimed that your best bug fix is time. And what I did here was that I looked at some research. And what the researchers have done is that they simply looked at different modules, that solve similar problems, and then they looked at the age perspective. And they found out that code that's been stable for 1 year has roughly 1/3 fewer defects than code that has been modified recently. And this is fascinating, because what it means to us is basically that from a quality perspective, from an external quality perspective, old code is good code. And the reason I say that is because code grows old for 2 different reasons. First of all, it might simply be that it's unused, right? It's dead code. And dead code is some of the best code you can have, because you can simply delete it, right? It's always a win to delete code. Or code grows old because it's stable. Maybe it's still hard to understand, could be potentially hard to maintain, but what is there is likely to have been debugged into functionality. It's been battle tested, it's been proven it's in use, and it just works. And using hotspots, you can ensure it stays that way, because hotspots help you sort your code base into stable parts versus the more volatile parts, so that you can focus a limited time on the parts of the code where you're likely to have the largest effect. Now, when we talk about technical debt, we also need to touch upon legacy code. I have found that quite often those 2 concepts are used interchangeably, but legacy code is something different. Technical debt is not legacy code. So let's take a step back and see what legacy code actually is. And the definition I use for legacy code consists of 2 different parts. Because I view code as legacy if that code lacks in quality to some degree, and more important, we didn't write ourselves. If we tick those 2 boxes, what we have is legacy code. Now, let me share a story with you. So this is something that happened maybe 1.5 years ago. I did some work with a client, and I got on site and I worked with one of their teams, and that team, they were responsible for 2 different code bases. So we did a hotspot analysis on them, and we started to review the code, we started to discuss the design, and what we found was that both of those code bases, they looked pretty good. Because those hotspots, any one of them that we picked up, it looked pretty good, right? Easy to follow, easy to extend, wonderful. So everyone was happy, but then someone shared the information that, you know what? We actually have 1 more code base here that we are responsible for. So I said, perfect. Let's bring it up and do a hotspot analysis of that one too. Yeah, but you know, it's a complete mess. I said, even more interesting, right? Let's bring it up and let's have a look at it. So we did. So we did a hotspot analysis of code base number 3. And guess what I found? It looked really, really good. It looked just as good as the 2 other code bases. There was virtually no difference in terms of internal quality. And this was surprising to everyone there, me included, until we realized that what had actually happened was that those 2 code bases, the first 2, they were written by the team themselves. The third one, that one was implemented by a different part of the organization, a different department, and this team have simply inherited that code. So the reason that code was deemed as complicated and hard to understand had nothing at all to do with any properties of the code. It was just unfamiliarity. And this made me thinking that ease of understanding is also about system mastery. How well do we know our code? And that got me thinking, how quick can we take our current code base and turn it into legacy code? What do we need to do? Let's find out by doing a case study. Before I do that case study, we need a way to reason about system mastery and knowledge distribution. And what I'm going to use now is that I'm going to return to the Git logs. Because looking at Git, we can get this kind of social data. We can simply identify the main developer behind each module. And the main developer is simply the person who has written most of the code. And we can sum that up, right? So let me show you a different code base. We ripped through our Java code base. Let's have a look at our .NET code base. So this might be a code base that a lot of you are familiar with as users. This is ASP.NET Core MVC from Microsoft. Is anyone using that framework right now? Lots of you, like 10% maybe, cool. So ASP.NET MVC is simply a framework for Microsoft for building dynamic web applications. And the visualization you see here, it's the same visualization style as we use for the hotspots. It's something called enclosure diagrams. But now the colors carry a different meaning. Because blue simply means that these are parts of the code that's written by people who are currently contributing to that code base. So people are now part of the team. The different shades of gray, those are our black holes in terms of system mastery. So these are parts of the code where the main developer no longer works for us, right? And what I did now was that I identified one main contributor to that code base, a single person, a person who works for Microsoft full-time on that code base. And I pretended, what's going to happen if that single person leaves? I mean, after all, there are like 180 contributors in total. So for sure, a single person shouldn't make that big a difference. Well, let's have a look at the visualization to the right. See the red areas there? That's the part of the code where we lose the majority of the detailed knowledge if a single developer leaves. Should we be worried? Yes, we should. And this is not a fluke. This is something I see consistently across many, many code bases in the industry. The interesting thing is that once we start to measure and visualize it like that, we can actually use this data proactively. So let's say this happened. Let's say that person, I just made up that scenario. For all that I know, that person is still contributing. But let's say they were really going to leave. What I would do in that case, if this was my project, my code base, is that I would use the time that I have left with them. Maybe they have 2 weeks, 1 month until they actually leave. So what I would do is, first of all, I would look for entire packages where we tend to lose the knowledge. So in this case, you might see here, there's a package called integration tests, where we seem to lose the majority of the knowledge. I don't know, maybe integration tests are important to us. If that's the case, what I would do is I would look at the other people who have written the rest of the code, and I would talk to them and would check, are you comfortable in taking over the maintenance and ownership of this package? What I would also do is that I would start to correlate this social data with our technical metrics. In particular, I would start to look for hotspots where we lose knowledge, because a hotspot is a signal of relevance. So if it's a hotspot, it means it's very likely that we will continue to work with that part of the code. And if it had some quality issues, then that's a big offboarding risk to us. So what I would do if I find something like that, like abandoned hotspots, is that I will pair together the person leaving with someone that's going to stay, and I would have them refactor that hotspot together so that we mitigate an upcoming offboarding risk. So what I find so fascinating about this is that there's so much more to code complexity than just properties of the code. And in particular, all these social factors like knowledge distribution and system mastery, they influence how we perceive a code base. And in particular, we tend to overestimate the complexity of unfamiliar code. Now, I have much more stuff that I want to share with you, but before I do that, let me share the kind of tools I use to do this kind of analysis in case you want to try it on your own code base. Now, you have to remember, this is still a pretty young field. When I started to do this kind of analysis, maybe 9-10 years ago, there weren't any tools available that could do the kind of analysis I wanted to do. So I had to write my own. And I open sourced my first tool suite. It's available on my GitHub page. And I still do the occasional maintenance of it. It's called CodeMat. It's completely free and could do most of the analysis that I show you today. What I work on right now is something called CodeSyn. So CodeSyn is an automated service for all of this. It's entirely free for open source projects. So if you work in that space, consider to have a look at it and support it. Now, what I also find so fascinating is that you can get really, really far with just a Git client. And I have many examples in my book, but I want to show you my absolute favorite. Did you know that with git log and the -l flag, you can specify a function inside a file and have Git trace the evolution of that function? That's basically like a simple X-ray directly from your command line. Now, you're going to get the links at the end as well. For now, I want to scale up some of the stuff we have talked about and see how we can analyze technical depth and non-code properties in microservices. So let me ask you, how many of you work on a microservice system? So it's like maybe 20% maybe, so a significant chunk. I find this really, really fascinating because when I started to work with code analysis 4 years ago, most organizations that I visited, they had some kind of legacy migration plan. They were talking about microservices. They have started to do the first explorations, but almost no one had them in operation. Today, microservices are mainstream. And this is interesting to us because what it basically means is that tomorrow's legacy systems are going to be microservices. So let's stay a step ahead and see how we can make sense of microservices. Now, when applying these techniques that I've shown you to microservices, we tend to run into a number of challenges. Some of them are practical, like microservices. They tend to be polyglot code bases, right? They also tend to be distributed in multiple Git repositories. But those are pretty easy to address, and I'm going to show you how it looks soon. What I find more fascinating is that in a microservice architecture, the most important aspects are not necessarily properties of the code, but properties of the system. What do I mean by that? Well, what I mean is that in a microservice architecture, code quality definitely matters. It does in all systems. But what's even more important are what does the connections between the services look like? How do they communicate and collaborate? And also, what does the people side look like? What does the team coupling look like? Do we have dependencies between people? So let's see how we can address that. And let's start by having a look at a system called Spinnaker. So Spinnaker is a continuous delivery platform developed by Netflix and now Google. It's a microservice system, and it consists of approximately 35 different Git repositories, each one of them encapsulating one or more microservices. And what you see here is a hotspot analysis of Spinnaker. So each one of those top-level bubbles is now an entire service, right? A separate Git repo. And the way I do this in practice is simple. I run a hotspot analysis for each one of the Git repositories, and then I just combine them in the visualization. Another thing I want to point out, and this is also why I'm such a big fan of version control, is that Spinnaker is implemented in many different programming languages, 7 different languages. And the fascinating thing with the hotspot analysis is since it uses version control data, it's actually language neutral. So we can visualize hotspots even in polyglot systems and get a holistic overview of them. However, I have found that in microservice systems, and we could of course use this to identify hotspots, right? We see a big one there to your left. But I have found that in microservice systems, the interesting level of analysis tends to be the service boundaries. So what I tend to do is I take all contributions to a single service and I simply sum them up and visualize hotspots on the microservice level. So this is data that we can use to detect services that seem to grow too complex, like deck here, which might be an indication of low cohesion and maybe too many responsibilities stuffed into a service. So this might be a starting point, but I do think that we need to do better, because a hotspot analysis won't help us in answering what's happening between the services. What about their boundaries? So we need to do a dependency analysis for microservices. And this is how a dependency view looks between the microservices in Spinnaker. And I'm going to show you how I do this calculation. We're going to return to this graph in just a minute. So how do you get the dependencies between microservices? They are located in different Git repositories, right? There's usually no direct physical dependency between them. They tend to be decoupled by networks and message buses and whatnot. So what I use is I look at coupling based on the collective intelligence of the contributing developers. I use a concept called change coupling. So with change coupling, what I do is I simply look at when we implement a new feature, what kind of stuff has to be modified in order to fulfill that feature. And in this example, you see a simple system with just 3 different microservices. We see that when implementing new features, the subscription service and sign-up service tend to be changed together. So if this is a trend that would continue, then I know that there has to be some kind of relationship between the sign-up service and the subscription service because they keep changing together, right? So this is what I did for Spinnaker as well. So the dependencies you see here are the dependencies of change. It's the impact of change. It's the change coupling. Now, how do you read this data? Well, the different labels that you see, each one of them represents a service, and the connections between them represents the change coupling. The colors of the links represents the trend. So red, in this case, shows a change coupling dependency that is growing stronger, right? So that coupling is stronger now than it was a month ago. And when interpreting this data, I see that there seems to be a cluster of microservices in the upper right corner that tend to be changed together. But what immediately draws my attention is this connection between bakery and Roscoe, whatever those microservices are. And if this was a system that was under my responsibility, what I would be interested in was to find out what does the team dimension look like? Because it's a big difference if those two services are owned by the same team or if they are developed and owned by two independent teams. Because in the later case, what this would mean is a lot of potential coordination and communication overhead. In particular, since that dependency is increasing in strength. And by uncovering this, we can start to answer one of the most common questions I get when I talk to clients. And that question is, should we use component or feature teams? You know, we kind of tried both and none of them really seems to work. So the reason for this is because in an architecture with tight coupling, with tight change coupling between different parts of the code base, if we try to go with something like component or domain teams, what tends to happen is that we get very, very long lead times. It simply takes a long time to respond to change because we need to coordinate across team boundaries. So maybe we decide to switch to feature teams instead. And again, in a tightly coupled architecture, what tends to happen with feature teams is that the whole system turns into a gigantic coordination bottleneck, which is an even worse problem to have. And I don't think there's any easy fix to this, because I think that the question of component versus feature teams, it's simply the wrong question to ask. Because we cannot fix what is fundamentally an architectural issue with organizational changes. So what do we need to do instead? Well, we need to strive for locality of change. So let me try to explain that by reading one of the best quotes I know about this subject. It's from a new book by Gene Kim called The Unicorn Project. Really good book, really recommend it. And in that book, Gene Kim says that simplicity is important because it enables locality. And locality in our code is what keeps system loosely coupled, enabling us to deliver features faster. So what's fascinating about this is that locality of change is not just a technical property. It's something that's fundamental to the business as well. It's locality on all levels that help us do things like time to market, to explore new features, to do experiments. And locality of change implies an alignment between our architecture, our organization, our teams, and the business problem we are trying to solve. And using a change coupling analysis like that, we can identify dependencies that violate the locality of change principle. Now, once we have identified those, so here we have Roscoe and Bakery, for example. Once we have identified those, we need to dig deeper and make this information actionable and try to find insights into why does this happen. And so far, I have ripped through a number of open source code bases. So I think at this point, it's only fair that I start to criticize my own code. So let's have a look at the system I worked with a couple of years ago. This is part of what later became CodeSyn. So what's fascinating with change coupling is that you can do it on any level of detail you want. And what I do when I find a dependency between different architectural elements is that I do the same change coupling analysis on a file level. And again, we are in version control wonderland, so we can do language neutral analysis. So in this case, we see we have a dependency between a piece of code implemented in JavaScript, part of the front end, that changes together with some closure code running on the back end. Now, when I saw this, and did this analysis the first time, I got surprised. And the reason I got surprised is because I happen to know that the code is actually structured this way. There is some distance, some kind of architectural distance between the two units that change together. One of them is front-end code in one Git repository, and the other one is part of the actual analysis, stuff that pulls out data from Git and does some calculations on it. But as you see, there is some architectural distance between them. So this was surprising to me. And as you know, surprise is never a good thing in a software architecture, right? Might well be one of the most important, most expensive things you can put into it. So what I did when I found this was that in order to make this actionable, I wanted to figure out, okay, so I know this relationship between the files, but what functions actually change together? So I did an X-ray analysis here as well, and I want to show you how it looks. So what I found here was a JavaScript function that changed together with some specific function in the closure backend. And what I found so fascinating was that when I looked at the code, I figured out that the backend code, what it did was actually it took some data from Git, did some calculations on it, and then it populated a result structure. And each time I added something to that result structure, I had a predictable change in the user interface as well to visualize it. So I know what you think. Not really a prize-winning design. Oh, maybe not. So I thought so myself, and I thought, how can I avoid having those two files coupled to each other? The lifetime is coupled. So I thought maybe we could do something like, like composite UIs. Maybe we can have some intelligent view models that kind of knows how to render themselves. And yes, we could. And if we would implement that, that change dependency would actually go away. But I don't think that's the right approach. Because I think by doing that, we would again be patching over symptoms and not the real root cause. And the reason I say this is because what we have here is a very classic dependency. It's a classic producer-consumer relationship, right? So it's very common. And when I think about it a little bit deeper, I kind of realize that those two modules, the reason they are kept in separate repositories, the reason they're implemented in different programming languages, is entirely accidental. One of them happens to be code that executes in a web browser, so we want it to be JavaScript, and the other one is something that executes on a server. But that separation is purely accidental. It has nothing at all to do with the actual business problem we are trying to solve. So I thought, what about putting them together? Let them be part of the same logical component and enable locality of change. So I want to leave you with a thought here before I take questions, because I do think that in the time to come, we need to take this a step further and let features drive architectural building blocks, not technology. And if we manage to align the boundaries in our architecture of the concepts from the problem domain, then we're enabling locality of change, which in turn benefits not only lead times, but also things like team coupling and teamwork. So locality of change is an enabler. And I do think that behavioral code analysis and these techniques for prioritizing technical depth have a place here because they give you insights that you cannot get from the code alone. If we look at the code, we cannot see change coupling. We cannot see social properties. And we really, really need them to be able to scale up with our systems. So the main use case I see for these analyses is that they don't necessarily solve any direct problems. What they do is that they help us focus our expertise and our attention to the parts of the system that are likely to need it the most. And if you want to read more on this, I have my new book, Software Design X-Rays. I blog regularly at ampere.com and adamtornhill.com. And I'll be hanging around for today and tomorrow. So if you have any questions after the talk, I'll be more than happy to discuss it with you. Now, I just want to take this opportunity and say thanks a lot for showing up at my session. Thanks a lot for listening to me. And may the code be with you. Thank you.